Okay, all right. Thanks, guys, for being patientful to get through this all that technical hassle. So I'm Prasad Venkatachar, and thanks for joining my presentation. And I have got a catchy title for the end of the day to see if I can create some interest with you guys to how to take your Percona server for MongoDB to the next level. Little bit about myself. So I'm working in the database analytics field for last 20 years. I've switched throughout my career. I kind of worked on different roles from a DBA to DBA manager, moved on to solution architect, and now onto the product management, building database and analytics solutions. So as part of this career, I kind of did all the database, big data, and cloud certifications. About my company, I work for one of the fast-growing startup in the San Jose, California. It's called Pliops, and we have an ambitious goal of accelerating all the database and big data workloads, and massively reduce the infrastructure cost. That is catching a lot of traction with the cloud providers, both in the infrastructure as a service and the software as a service, cloud providers. And on the vertical side, on the enterprise, we got good traction in the manufacturing and the e-tailer and high performance segment, HPC. So high level, I'm going to talk through what is the, all the testing and the good work we have done and the best practices we have employed for coming out with these good results with the MongoDB. And feel free to ask any questions. With that said, as I said, as a DB manager or a solution architect in the past, when I used to engage the business team used to reach out to the IT team, they always ask, I have to roll out a new services, new cloud services or a new application, and my users will be somewhere around 5,000 starting today, and it will scale to 10,000 within 3 months. And you got to meet to the IT SLA compliance on the performance and the availability, all the 4 nines SLAs. You got to take care of it, and the customer satisfaction is customer experience. Customer CSAT score is another key criteria. But when you from the IT side, whether it's a shared IT or a central IT, so the key things you'll be looking at, this is your data. What kind of a data I got to store in my this one in database, and what is its growth, and what kind of performance I got to take care of it to meet the performance and availability goals. And then, of course, the infrastructure cost, as the cost of this infrastructure, the database is growing, your infrastructure is growing. So you got to think about how do I maintain my infrastructure cost and the software licensing cost. And more importantly, last 2 years, because of this COVID, the supply chain has become a big hassle. Even if you want to have all the IT budget that you have, but you can't procure enough hardware because of the huge, the delays in the supply chain. So there is a new ways of looking at. You got to think about, how can I optimize my process, my infrastructure, so do more with what you got, right? So that's the goal. So with that, let's evaluate, Pliops benefits for Percona server for MongoDB. Probably if you're using, MongoDB with Percona server for MongoDB, there is a lot of benefits on the right-hand side. You get it from, the security, authentication, authorization, and manageability, observability from the PMM, and any of the operations in terms of the database auditing and backup. But when it comes to on the Pliops side, we were trying to explore, whether how can we help on efficiently storing your data in economically scaling it as well, and how can you address the performance and SLA goals, in terms of whether it is in IAPS or operations or it is in a latency reduction. And then database protection, right? Data protection is another important aspect. So all these 3-4 aspects combined, right? What does it mean for the IT budget? Can we help in improving or reducing the cost of infrastructure? So that was the objective of our evaluation. So we picked an identical server configuration for a baseline. So setting up a Percona server for MongoDB 4.4 version. And we use the industry standard Yahoo Cloud serving benchmark, running data loading, write heavy workload, read-heavy workload, and read-only workload. We also use the native Mongo gen for data loading and evaluated its performance, and also the Mongodump for backup and restore operations. So begin with on the baseline, like if you have a baseline on a RAID 10 setup, as per the MongoDB recommendation, you have to have the database running on the RAID 10, so for providing any data protection. So we picked RAID 10 on the left-hand side for a baseline with 1.92 terabyte of SSDs, and 4 of those SSDs will translate to 3.84 terabyte. When we loaded this data, right, like YCSB data, MongoDB with the snappy compression, which is the default snappy compression, it provides a 2.6x compression. So with that, like, you can load up to almost 9 terabyte of data set. You can store up to 9 terabyte of data set on the baseline. So on the right-hand side, like with the Pliops, we switched that RAID data protection from RAID 10 into RAID 5. And thereby, within the physical capacity itself, we increased the available capacity from 3.84 on the baseline to 5.76 on the with the Pliops environment. When we loaded this data set, you can see that here on the screenshot I'm showing here, like we with the XDP provides a built-in line rate data compression. As you start loading it, we have a compression engines built into it that will take care of all the the compression benefits. So compared to the snappy compression on the baseline, we increase the additional compression benefit with the XDP line rate compression. So with this, we are able to demonstrate or conclude that on the left-hand side, you can go maximum up to 9 terabyte of data set with the 2.6x terabyte of 2.6x compression. On the right-hand side, with the Pliops, you can go up to 12 terabyte. It's almost around 3 terabyte of additional capacity that you can get out of the system straight away, not doing any changes in this one. So then looking into the data load operations, so when we are loading around 350 million records, each objects around 1.1 kilobyte of object size. And when you loaded this, on the left-hand side, the operations, the insertion per second, like, it's around 25,000 operations per second. On the right-hand side, with the Pliops environment, we are shooting up to 48,000 operations per second. So that's an improvement of 1.9x higher operations per second. And on the right-hand side, like, for the latency side, so the latencies on the baseline, the software with the snappy compression, it's 0.3 millisecond, and we reduce that into 0.163 milliseconds. So the latencies has reduced by 51%. The performance has gone up by 1.9x. This is the additional further details on the same data set. You load it on the baseline 4 hours. The Pliops enabled environment reduces by 2 hours. So you can say 2x faster data loading. 110 gigabit of data set, you can load it per hour on the baseline. The same thing will improve it to 220 GB per second. So operations, I talked about how many operations and the latency. But when it comes to the disk I/O throughput, 169 MB per second been improved to 353 MB per second. And the CPU usage, there is a marginal additional 2% CPU usage we use it, but if you compare this into performance per core, like this system has a 40-core machine. Now each core on this, right, like it does on the baseline 3,669 operations per second, but with the Pliops enabled environment, it translates to almost close to 7,000 operations per second. So another 1.9x performance per core. So this is one way to illustrate. You can pick a lower end CPU cores to get the equivalent performance rather than, right, like going a high end CPUs to get that. And the same benefits, we have evaluated with the Mongo import. The test results I'll talk about in a little later slides. The same benefit, if you have your database MongoDB, you're using it for ETL operations, any data ingestion, change data captures, message queues. These benefits are seamlessly applicable from using a Mongo import, or if you are doing a bulk insert, bulk write operations or a change data capture. The next one, we are working with one interesting customer where here they're capturing all the orders in a real time that is coming from both the web orders and the mobile orders, and it is going through an order management. It will route that request into the Kafka. The Kafka here, we use the MongoDB, both the sink and the source connector. The Kafka messages is directly ingested into the MongoDB collections. And here then there is a lot of data aggregation pipeline, like building an aggregation, filtering, join, roll-up operations. So that way this company can see how many orders they are receiving per hour. They can track their inventory, or if they wanted to refill the inventory or come up with a new promotions based on the orders they're kind of receiving it, they can do that everything in real time. And this gets published to the downstream applications or any of the message or BI tools using the Kafka Streams engine. So that's one thing on the data ingestion. Now, if you go look this into, if your applications is somewhat a mixed workload with a 50% reads and 50% write, here the same thing we evaluated when we run this thing. This is much higher benefit than the pure data ingestion operation. So here on the baseline on the software Snappy, 30,000 operations per second. The same thing with the Pliops enabled environment that shot up to 70,000 operations per second, and that performance boost of almost 2.3x. On the left, on the latency side, so the latency is around here. The y-axis is in the microsecond. I'm converting into millisecond. The 4 millisecond on the baseline is reduced into 1.5 millisecond. So these are the further details about which I talked about, the operations per second improvement and the latency reduction. But when you look into the CPU, right, the data ingestion is you saw it's 2%, but in this case, in the write heavy workload, the CPU savings is 38% on the baseline, reduced to 32%. And the I/O throughput has improved from 763 MB to 2 gigabyte per second. So that's you see an improvement both in the I/O throughput as well as the CPU utilization has come down significantly. So the other the read heavy workload, where you have a 95% of read and 5% of writes. Here, even in this case, very corner case, where the performance benefit is like if you have a 68K operations per second, 68,000 operations per second, that improved to 80,000. And the latency again in this case also reduced from 2 millisecond to 1.6 millisecond. So here is the further breakdown of all the the performance and latency benefit. So in addition to that, the CPU utilization has reduced from 32% to 26%, and the I/O throughput increased from 1.6 gig into 2.4 gig. The last one is on the YCS-BC, which is like a completely read-only workload. Here we are kind of finding out, the operations per second is improved from 82,000 operations to 86, and the latency is reduced from 1.8 millisecond to 1.804. Here we are trying to understand what more can be done. That way we'll increase the performance benefit that we have seen in the previous two cases, where we kind of saw almost 2.3x and 1.9x and 1.5x. We are kind of looking into identifying other optimization areas. That way we can increase both the throughput and as well as reduce the latency. However, on the system resource utilization side, if you see here, again, compared to the previous scenarios, the CPU utilization has come down from 33% to 25%, and the I/O throughput has increased by 400 MB per second, higher compared to the baseline. So in a nutshell, what I was trying to highlight, now here, this is a further breakdown of all the three different tests we kind of carried out. So here, what you see here in the CPU utilization, we kind of breaking down into the user CPU, system CPU, and the I/O weight. The very important point I want to highlight here is on the baseline, which has got a software, using a software Snappy compression. the system is waiting for, the CPU is waiting for the lot of IO weights to be fetched from the wire-taker storage engine, passing back to the system. So that's why, in a YCSBA, there is 21% of the CPU is waiting for the data to be fetched from the IO. The same thing on the B and C. That is where we are kind of reducing it to a greater extent here, right? So and other point I wanted to highlight here is the user CPU. So when you run any workload, whether it is a MongoDB, MySQL, any of the things, you want your CPU to be utilized more into the user CPU. So that means you are putting your CPU to work or your systems to work, driving more throughput, because that's more, you're generating higher operations, higher transactions, or processing more queries. So that's where we kind of help in improving the user CPU utilization and reduce all the IO weight. And the bar charts on the left side, what we are trying to illustrate here is like, all these three, right? So comparing this CPU per performance per core. So if you have a 20 core machine, right, we provide almost 1.9x faster performance. So that means you don't need a 20 core machine to run that using the Pliops. You can reduce the 20 core into 10 core machine. Or if you're using a 40 core machine, each one is a 20 core, each CPU is a 20 core, you can reduce into just the 20 core, like use a lower bin CPU. So I have a math, I'll show how we kind of help out on the cost savings there. Yeah, sure.
So have you also done testing with TPCC benchmarking, or is it mainly limited to YCSB?
Typically, NoSQL, everything uses the YCSB benchmarks. That's the recommended. We also carried out additional MongoDB related tools to say whether, because these are tools that MongoDB DBS use. We use that tools also to evaluate the performance. TPCC, Sysbench, those things.
Yeah, TPCC typically used in e-commerce kind of workloads. So
Correct.
wasn't sure if you guys, because generally the performance is very different across YCSB and TPCC.
Yeah. So again, what we work with several. Throughout at Pliops, we're working with the 3-4 customers with NoSQL, especially on the MongoDB. Majority of them use the YCSB for evaluation, and TPCC, this one is applicable more for MySQL, MariaDB, because there you're counting on the transactions per second, and even SQL, Oracle, the same thing. They use either HammerDB or Quest Benchmark Factory and other things to evaluate the performance.
Mongo basically suits better with YCSB.
Correct. Mongo, Cassandra, Aerospike, Couchbase, so all these NoSQL distributed scale-out, everyone uses the YCSB.
Yeah, because if you think about the relational database has a specific schema, structure. I don't think that would carry over to Mongo, but they don't have the same table, row.
So. Yeah, MongoDB is more a schema-less, like in the sense like you can dynamically add the columns and like it's based on a JSON format, right? So.
The test was done over a cluster, a single node of MongoDB. How was the setup there?
We tested. Right now that.
Cassette or a single node?
So right now the results that I'm sharing is on the single node, but we had the customer POC scenarios that a couple of customers I talked about manufacturing and those things. They've carried, they're deploying in fact on the clustered environment, MongoDB clustered environment, both on the replica set as well as sharded cluster. So I got a slide about this. So the MongoDB Backup dump is something typically DBS use to offload the data, right? So we offloaded entire 3.2 terabyte of data set. We loaded from the MongoDB onto the file system. So on the baseline, it took around 102 minutes, and the CPU utilization 12.6% and 1.1 GB of IO throughput. The same thing, we ran that same unloading 3.2 terabyte that reduced from 102 minutes almost up to 61 minutes. So there is a 40 minutes of savings, right? So if you're not only loading into the database, unloading also we save significant amount of time. That's another. And the reason why we do that is because the I/O throughput, right? When it is unloading, it is writing that all the data coming from MongoDB into the file system, the XFS file system. We improve that I/O throughput 1.1 gig in the baseline to 1.7 GB this one. And the CPU utilization, as you see here, 12.6% of CPU is reduced to 9.17%. So this is a real data set like it is. The next one is in another. Yeah, so this is a data set we have loaded. And this is on the MongoDB. And the next thing is like, obviously, now you've seen the very first slide, we kind of did in a RAID 10 setup comparing with the RAID 5. The very fundamental question happens, like what happens to the performance when you lose a drive, right? Because RAID 5 is only can tolerate one drive failure. Then what happens? Because then does it trigger my primary database to go, the secondary will become a primary. So that is where the test we kind of carried out, like just to show. So one in the side, this side, if you see in the normal operations, we are clocking around 90,000, 95,000 operations per second. Then we simulated a drive failure, like let the drive fail, pull the drive, and and let this stay for an hour. Like you see here from 960 seconds all the way up to 4560. That is 3,600 seconds, which is like almost like an hour, right? So for 1 hour, we wanted to measure like, well, the performance goes down if I'm pulling a drive, like, what happens? So the performance stay the same, right? And not stay the same, like in the performance drop is less than 10 to 15%. And then after that 45, 60 seconds, like we initiated a rebuild. Now let's go rebuild an operation. And how does the rebuild operations takes the bandwidth, because it has to redistribute the parity, we put the new drive, it has to redistribute the data and everything. So what is the performance impact with that? So as you see here in initially when we kick off this, for at least maybe 45, 60 to 48, maybe around 15, maybe 15 seconds or maybe around 2 minutes, the performance is lower. It went down because it started calculating the parity and redistribution. And once you start rebuilding it, the performance came back to the same level as like, where you had detected the faulty drive. So the performance drop from the peak to when it is rebuilding is less than 10 to 15%. And we provide a flag for the users based on, because the customers that we are working with, they have a MariaDB deployment where they have the same scenario. They transition from RAID 0 to RAID 5 with Pliops. So they have an SLAs that they are attached to customers, whether they wanted a faster rebuild with losing some amount of performance, or doing an extended rebuild time, dropping very little in performance. So we have both kind of customer scenarios where that's why we provide a knob. Tell me your SLAs, what works for you, we will make that happen. Like this rebuild has got 2 knobs, faster rebuild, lower performance, faster rebuilds, drop in performance, little bit drop in performance, versus longer rebuilds, very less drop in performance. So that's the essence of this performance during testing. Then the Mongo import. So we imported around 770 GB of dataset. This is an Amazon review dataset. All the likes, comments, and everything you provide, like Amazon exposes as a kind of a file that you can go and load into any database. So we picked that dataset because it's a lot of real data, because everything, right? So when we test this thing on a baseline, it took around 83 minutes. And MongoDB doing the software snappy compression around 2x. The dataset reduced at 770 to 340 GB. And the same thing, I/O throughput 212. But in this case, on Pliops side, this reduced to 80 minutes, 83 minutes to 80. The drop in the duration is not that significant. We are trying to identify what is the reasons where we could go and improve this, the import operations. But at the same time, what you find it interesting here is this is a df-h on the command down. You see on the baseline with a 10% of data set, right? It took around 347 GB. So now if I make this data set completely 100% of this file system, I can go load up to 6.9 terabyte of data set. On the Pliops side, the same thing. You can, with the 7% of utilization, want to load it up to 100% of the utilization, we can go up to 12 terabyte. So the additional space savings, if you are loading at a completely utilizing your all the available space, with the Pliops, we provide another 56% more capacity. So on a single server, no changes required. Switching from a RAID 10 to RAID 5, and enable, from a snappy compressions to XDP compression, you get the additional 56% capacity. So then the last one here is I don't have the data on the MongoDB, but it is pretty much same on the same related to the what we have tested on the MySQL using the Percona PMM thing. So the write amplification. What is the write amplification? Is the amount of data that is coming from an application to what is writing into an SSDs. Typically, there is a amount additional data. It will go and write it because the way there is a some kind of a IO overhead it adds, and SSDs has some definite P cycles, program error cycles. So if you have spec the SSDs or whatever you purchased for 3 years, because of this write amplification, it is writing 2 times more or 3 times more. If you're using, if you wanted to use this infrastructure for 3 years, probably you might be running out within 2 years or even a year itself. So you got to go and buy a lot of this flash storage to make sure you can use this infrastructure for 3 years. So there is a lot of storage cost involved. In addition to the compression capacity savings, the endurance savings is phenomenal, because one of the customers that I'm working with, we are kind of helping them to switch from a high performance drive into a low performance drive, number of drives into this, just improving the write endurance. So thereby, the 2 SSDs and a high density configuration for a 30,000 servers, they are seeing around 7 million of savings. So just on transitioning from a high performance drive to a low cost drive, the cost savings is phenomenal. So here is the another the customer that I was talking to, or is deploying. This is a manufacturing customer. They have not a sharded, like the replicated setup on the primary and 2 secondaries. And here, what they see is a performance boost not only on the primaries, but even on the secondary, because there is in MongoDB in there is something called a op log, so which is captures all the data, the transactions or writes that is happening, so that the secondary will catch up in synchronization. So the op log that is getting applied onto the secondary has gets without the Pliops, it takes a lot of the delays in getting this these changes being committed from the primary onto the secondary. And that was causing a lot of delays in terms of secondaries not being responding to all the the reports they wanted to generate. That was one other point. And there's another thing is like in the MongoDB there is something called checkpoints. It happens at 60 seconds or 2 GB of data set is being loaded into the Whitaker cache. That is to go and flush into the SSD. So this happens very aggressively if you have a lot of writes, and they have seen a performance boost because we write to this SSD in a compressed format, and we know then the boundaries how we need to go write it, convert this all the data in from a random into sequential, and there also we are helping the performance. So the checkpoints for the natural MongoDB operations is also helping them to improve the performance. Third one is now they are expanding this into from a replicated into the sharded environment. They are kind of creating a sharding key, and here they see a significant boost because when you shard a key, the data has to redistribute based on the shard key you select, and there they see that when you shard, there is a rebalancing. that they have seen a benefit as well. So these are the 4 areas that they have seen. I mean, I do not have a metric to attach to each of these, but the benefits they have seen even on the scale-out setup, whether it is on a replicated or a sharded cluster, is significantly helping the customers. So summary of findings, what we have seen is the capacity savings, as I said, like, a 40 to 50%, switching from a RAID 10 with the snappy to Pliops RAID 5 with the built-in compression, and the data ingestions, whether you're doing an ETL operation, streaming, or any of the Kafka data loading from this, that performance is improved by 1.9x. And if you have a write-heavy workload, the latencies also gets reduced. The performance goes up by 2.3x. And the latencies for a mixed workload, I mean read-heavy workload, reduced by 50%. And the CPU per core has increased by 1.8x. So just to put the simple math on the here, so if you have an average server price around 30,000 you spend on with the SSD, memory, and everything, right? And you 10 servers. With this 50% of savings, we get drive more than 50% saving. Even if you consider a 50% of savings, so that 30,000 you can consolidate or reduce the string the 10 servers into 5 servers, and reduce your capital expenses from 300K into 150K. So it is a very simple calculation because we are working with one of the order management system we are kind of working it. There they are kind of looking at so hundreds of MongoDB nodes. There the savings we are talking in terms of millions, where they are looking into reduce their footprint. So at a high level, so like Wiretigger, if you use other databases like MySQL and other things, as InnoDB, if you use a Redis, there is a RocksDB. So typically it uses the CPU for doing its own compression and also the amount of I/O amplification. That means what is written from an application, whether it is a database or a big data on this one. But eventually what it writes to an SSD, it will have an I/O additional data which it is going to write. That means that those underlying infrastructure will wear out quickly, or you have to refresh it very often. And if you have anything on this layer, which is a storage management layer, if you want to provide a data protection or data sequentialization, because we convert all these data from random to sequentialization. So if you are using any of these, the softwares on top of it, so from a direct attach or all-flash array, the additional CPU, you will end up consuming it. So what we are thinking is you can reduce all these different storage engines into offloading this into Pliops, right? We kind of collapses minimizes the write amplification to theoretical levels, and eliminate all these CPU overhead and everything to a significant level. So right now, all the benefits that I've talked about, we operate in 2 modes. One is a block mode. You plug in our product, it will expose as a block device, and all the data that is coming from MongoDB or MySQL go through our card, and we write into SSD. So then we also have another called a key value interface. Here, if you have applications like, for example, Redis, or even MySQL has MongoRocks, some of those key value based applications, we can provide this performance benefit immensely. That's in the order of 5 to 6x, right? Like here, this is where I was testing one of the Redis application. With the RocksDB, it was running around 23K operations. More importantly, the standard deviation. You see 32% of the standard deviation. That means the performance is not same, linear, right? So there is a lot of spikes going in and up. And whereas the same thing, running this with an XDP environment and a key-value interface, you not only get a 5x or 7x performance boost, but the performance variation is only 2.3%. You get a very consistent performance throughout the entire operations. So this is further to highlight the amplification that happens whether using different types of SSDs. This is the left-hand side is a standard high-performance SSD. But many of whether you talk to Facebook or Twitter, any of those things, there process billions of objects, tiny objects. These are almost like 100 bytes. But when you go make that change into the 100 bytes and go right to an SSD, which operates at an indirection unit of 4K, 100 bytes, now you have to go and write into 4K. So there is a 40x I/O amplification. So that is where the benefit of writing it, converting the smaller blocks, streaming, making into the data sequentialization and writing efficiently will save a significant amount of storage overhead. And the same thing on the high capacity here on the QLC. Even if you change the object size from 100 bytes into 1K, the QLC, which is a the high capacity, lower cost drive, the I/O amplification is 64x. So there is a significant amount of I/O amplification happens depending upon kind of average object size and depending upon which applications and what is the object size you're using, and you incur a significant cost. So here is what we provide is an XDP KV. This one, it is completely 100% compliant with the RocksDB KV library. And if you have any of the applications using Redis, Cassandra, or document database like MongoDB, object stores like SAF and those things. So we provide, and this provides a orders of magnitude improvement in performance, and that will help you to take care of, it's 100% compliant. Whatever the operations that is coming from the application, get, put, multi-get, range operation, everything will take care of it under the hood. So thereby, we not only improve the performance by 7x, 10x, this one reduce the latency, and you can also utilize that benefit into, if you're looking at a high infrastructure, like for example, so here, actually this is a SaaS provider for the MariaDB. So the same benefits what we are trying to highlight on the MongoDB, right? Like, so the benefits, what you see on the left-hand side, what you get on the 9 terabyte on the RAID 10 gets reduced into 16 terabyte on the right-hand side with the MongoDB, the Pliops. So you get almost, increase this, reduce that TCO per terabyte by 30% and improve the performance and average around 1.5x. And more importantly, if you want to go have a lot of multi-tenancy, increase number of MongoDB instances, you can increase that by 46%. So, and SSD endurance savings, as I highlighted, is another significant factor, which will save, depending upon how much density you have, it will save several millions of dollars if you're looking at a 30,000 servers and that kind of a high footprint. So this is another customer scenario I was trying to, the order management system, they have a huge MongoDB deployments, hundreds of MongoDB instances. Their objective is like, so how could I improve, because they have scaled this to match the 4.9 latency, not only on the performance and the capacity, the 4.9 latency, because they want to make sure that 99.99% of the users get a consistent low latency the moment they plug into either a mobile website or they're logging into the desktop. So they get a consistent, so that they can process these orders. So thereby they had to add a lot more number of nodes so that there is no tail latency. So we are kind of helping to minimize all those tail latency. With the 38 servers itself, we'll get the 100 node of MongoDB instances. So here the significant cost savings runs into several millions as well. So here is where my summary slide, like if you're using a Percona version of MongoDB, Percona server for MongoDB, complement all the benefits that you get it from the Percona server, from the manageability, encryption, security, and operations efficiency, taking the hot backups. We complement with the capacity, performance, latency reduction, and economically scaling your footprint. So thereby you will look into saving infrastructure cost reduction or running the same infrastructure at a 2x or a 3x faster speed and accommodating for all your future growth. With that said, I think that's my last slide.